Hey all, how's everyone doing? Today we're doing kinetics, so energetics, and equilibria. So this is going to be stuff. Basically, we're just going to run through Maxwell Boltzmann distributions, collision theory, temperatures, concentration, pressure, catalysts. And then we are going to do Newton's law, is that energetics? It's not kinetics, is that? And then we're going to do equilibria as well. So a couple of things today. Equilibria, just KC, KP, basically just touch on that and understanding like the factors that affect KC and KP. So getting you like familiarized with that. And I'm thinking with equilibria, we can also do Le Chatelier's principle there as well. So basically, not too much, shouldn't be too difficult. And hopefully today we can get onto some exam questions at the end. We've got a couple more people in the waiting room. Today's turned out slightly better than kind of the biology session. Just a reminder, there are free biology sessions on every Sunday. Right. If we're ready, we'll give it a start in about 2 minutes. I'm just going to keep an eye on the chat as well, again, as usual, as standard. Right. Cool. Now let's give it another minute. We can still see people come in and join in. Right, let us get going. Cool. So hopefully everyone can see my screen. Let me know if you can't, if there are any problems. So we're going to start with collision theory. So this is kind of the basics of kinetics. And basically the spec points that we're going to be trying to tick off today is, what is the definition of activation energy? Basically an understanding that reactions can only take place when collisions take place between particles having sufficient energy. So remember, we've got two requirements. Collision needs to take place. Particle needs to have sufficient energy. This sufficient energy being called the activation energy. And so therefore, based on that, we should already be able to have a chat about why most collisions therefore do not lead to a reaction occurring. Yeah. So starting with the definition of the term activation energy. So I'm sure all of you have seen this reaction profile diagram before. It's kind of the indicator of how a reaction progresses. So this, we've got which type of reaction? Where the energy is, where the product's energy is higher, lower than the reactant's energy. Sorry. Anyone give me a guess? Exothermic, yeah. Perfect. It's an exothermic reaction. So the activation energy is defined as the minimum amount of energy needed for a successful collision to occur between particles. So basically, it's an understanding that even though these reactants and products are at this energy level, that is the energy level at which they are stable. So these reactants are going to be sitting in this energy environment in a position of stability. They're not going to be wanting to react. But once their energy state has been lifted into the activation energy, which is here, that begins the process of this reaction occurring. So it's basically the reactants start stable and they then need to be given the energy to take them to the activation energy, which is basically the minimum amount of energy needed for a particle or a successful collision to occur. A successful collision is one that leads to a reaction. So understanding that successful collisions basically always lead to a reaction. And this therefore represents the energy barrier that reactants have to then overcome to be able to react. Does that make sense? So understanding that basically for a successful collision to occur, you need two things. You need a particle that is at the high energy state, obviously, and a particle that is in correct orientation. So a particle that's turned in the correct way. Why? Can anyone think from a biological sense? I don't know how many of you take biology as well. Why we need both of these things? And what example of a biological molecule that wouldn't work if it was orientated in the wrong way? Enzymes, yeah. Enzymes are the perfect example of this. It's the same sort of principle that we're going to talk about here can be applied to enzymes, is that generally molecules need to react so that the correct areas and the correct parts of the molecule that are going to be denaturing, not so much, but the correct parts of the molecule that are reacting are in the right complementary pairing, yeah, those kind of things. So if we imagine a molecule that is, let's do something, a simple reaction. Let's get you NH3 is a product of the Harbour process. So it's where H and H hits N and N. Would this reaction work if the N was sort of coming directly between the two H's? Would this reaction work? Probably not, if we think about it, because that would not break the bonds with the right, it's not in the right orientation to break that bond that's needed to be broken. Whereas if it came from a different direction, perhaps. So the principle is that you need both the correct orientation as well as the right amount of energy, which is the activation energy, to lead to a successful collision. And therefore, that is the collision theory, is that particles must collide with the correct orientation and enough energy to break the bonds between reactants in order for a reaction to work. So remember, the correct orientation is needed to form or break the correct bonds. And it also is just to stop the molecules from bouncing off each other. Because remember, if they react with the molecules just hitting each other, that's not going to lead to a reaction. So it's to break the correct bonds or break or form the correct bonds, or to prevent them from bouncing off each other. And the activation energy, again, sufficient energy is needed to basically allow the correct bonds to break. Remember, bond breaking needs energy, bond forming releases energy. So therefore, a reaction with low activation energy will happen more easily than a reaction with high activation energy. A reaction that has a high activation energy requires a larger amount of heat energy to reach that correct point that is needed for the reaction to be able to occur properly. So as you can see, activation energy. So this reactant, if it was, say the activation energy was up here, this is going to be a significantly more difficult reaction to occur. Yeah, because as you can see, it needs more energy to get to that point. Okay, and so remember that most collisions don't lead to a reaction, because even if they were high energy but they were wrong orientation, that's unsuccessful. High energy incorrect orientation. Sorry, I think they've got this the other way around. So let's exchange that. High energy correct orientation is obviously going to be a successful reaction. So it needs both the energy and the orientation to lead to a successful collision. A low energy unsuccessful, low energy but in the right orientation isn't going to do much either. So remember, if they do not collide with sufficient energy or in the correct orientation, that's going to lead to an unsuccessful collision. So that's the basics of collision theory. Does that all make sense? Yeah, cool. We good to move on? We're now going to talk about Maxwell-Boltzmann distribution, which is probably slightly more challenging for most of you. So this is probably a very new thing. So remember, Maxwell-Boltzmann distribution shows the distribution of molecular energies in a gas. So what it does is it's some sort of diagram to represent how all the molecules have different amounts of energy. So remember, not all of the molecules in a gas are going to have the same amount of kinetic energy, because the kinetic energy depends on how much heat they've been applied to, but also other factors, including how many collisions that they've done, how many other things that have happened to the gas particles within that environment. So the Maxwell-Boltzmann distribution is trying to put this into an image or into a perspective. So it represents the distribution of these molecular energies in gaseous state. And therefore, as energy increases, the number of molecules at a particular point is also going to increase gradually, and then it's going to begin to decrease. So basically, understanding that the three key points to this is that it always starts at 0, 0, because no particles have no energy, because then they would literally not physically be able to do anything. No gaseous particles will have 0 kinetic energy. The second point is that it never touches the bottom. So your graph should never touch the bottom, because some particles will have up to almost infinite amount of energy. And remembering that there is now the median particle energy is kind of halfway through. The mean is going to be to the right of the median, purely because the mean is always usually higher because of the fact that it's distributed more that way. Because remember, it can almost go all the way to infinity, kind of, as you keep going along. So the mean particle energy is always to the right. How can it can't have infinite energy, it can have almost infinite energy. So it can have as close to infinite as you can get, because infinite is not a number, which is the problem. And then you've got your activation energy, which again is to the right of both of these. And so as you can see, that demonstratively, there's a very small proportion of particles that have got energy greater than the activation energy, which is perfectly reasonable, because it shows why reactions don't happen generally that frequently, right? It shows that reactions don't happen like all the time. And so that kind of makes sense. What's the definition of Maxwell-Boltzmann distribution? There's no definition. It's not a term. Maxwell-Boltzmann distribution is not a term. It's a diagram. The image is the definition. It's a recognition of the fact that particle number of molecules change with the particles, and how that changes with the different factors. So there is no real definition to it. Does that make sense? So what does the area under the curve represent for this? Anyone know? The total number of molecules, yeah. So the total area under the curve represents the total number of molecules, or the total number of particles present. What does the activation energy is represented by a dotted line, remembering that. The shaded area is going to be the area with to the right of the activation energy, which represents the particles that will react when they collide. So basically particles with energy more than the activation energy. The median is represented by the peak of the curve. Sorry, other way around again. And the mean is to the left, to the right of the peak. And this is higher than the median, as often very high energy particles will be present, which are going to distort the mean slightly. So that's what I was saying, basically. Some particles will have as almost an infinite number of energy. So that's going to shift the mean very much to the right. Whereas, remember, no particles can have less than 0 energy to shift it back to the left. So can we all have a go at labeling these? Just if you state the colors and kind of what that represents, that would be perfect. Line at the peak is median. Give us some, please, could you give some examples of particles with almost infinite energy? No. It's not, there's no specific particles with more than an infinite amount of energy. Any gas, so this is to do with gas laws. So any gas that is spread out at a, let me explain this on a whiteboard. So we've got a gas at, oh, sorry, you guys are all correct. I'm just going to draw this explanation out. We've got a gas that's being heated up, right? And as this gas gets heated up, it gains energy, right? So as it gains energy, it's going to gain energy. And we know that some of these, whatever gas this is, this doesn't matter. It's not a specific type of gas. Whatever the gas is, at specific, as it's gaining energy, perfect, yeah. As it's gaining energy, some particles are going to start colliding with the walls, which means that they're going to lose a little bit of energy as they collide with the walls. But some particles won't collide with the walls. So they're going to still continue to have a really, really high amount of maximum energy. I think I've confused people by calling it almost infinite energy. It's not a specific type of particle that has almost infinite energy. All it is that some particles are going to not collide with the walls as frequently, so they might not lose as much energy. So they're going to have as close to the maximum, whereas some particles are going to, ideal gases don't lose energy when colliding. Most gases will. It's the same as if you imagine, kind of you swimming, right? I don't know if anyone has done, like anyone does swimming, but if you go swimming and you stop at the end where the wall is and you try and turn around, that generates more force again, but you have to generate that force again because you lose energy by stopping and then you have to restart by in the opposite direction. That's basically a collision with a wall. And so, yes, colliding with a wall normally will, in every realistic sense, is going to lose energy, even a fraction of it. But some will collide less frequently, so they're going to have quite a high amount of energy. Some are going to collide less frequently, more frequently. They're going to have a lower amount of energy. And that is what is represented by the Maxwell Boltzmann distribution. But it is the fact that eventually, you will continue, just keep going, like off the page even. There is no maximum amount of energy, basically, to any particle, any gas particle will have. Does that make sense slightly to the person who asked me that question? It's not that there are specific types of particle that have an infinite amount of energy. It's just that some particles of any type are going to have a really, really high amount of energy. Make sense? Yeah, I'm gonna take that as a yes. We'll go back to the slides. Okay, so you guys have all labeled them. Yeah. So that's basically the principle to the general Maxwell-Boltzmann distribution. Do you have any questions? Anyone have any questions about that so far? I'll wait a second for you all to just kind of breathe and relax a little bit, take some notes down, and we'll move on to the changes that occur with the different conditions. Any questions from Maxwell-Boltzmann? No? Okay. So, oh, can we go over forward? Can we quickly go over forward and reverse reactions? Yeah, that's going to be in Equilibria. So I will come to that. That's going to be straight after this. And that's the whole concept of reaching a point of dynamic equilibrium and all of those things. So that is kind of the topic we're going through at the end of this lesson. Okay, effective temperature. So the first thing we need to talk about is the meaning of the term rate of reaction. So a rate of reaction is the change in the amount of product, amount or concentration of either the reactant or the product over time. And that kind of makes sense, because if you imagine a reaction progressing, if you imagine just the general curve for reaction to progress, you start with a low amount of whatever the product is. It ends up getting higher. It ends up getting higher, and then it ends up plateauing, right? Because at that point, something else becomes the limiting reagent. Now, if we do that same thing with the reactant, it starts quite high. It gets lower as more and more of it is converted into product. And it ends up plateauing as well, the progress of the concentration. And so really, ideally, this rate of reaction is pretty much identical. It doesn't matter whether you use the reactant or whether you use the product, because the same rate at which the reactant the product increases is the same rate at which the reactant decreases. So overall, there is no net effect on whether reactant goes, whether concentration is going one way or the other way to affect the rate of reaction itself. So that kind of makes sense if you kind of imagine it. That's why we can use both reactants or products in it. So the rate of reaction can be calculated as a decrease in the amount of a reactant over time, or the increase in the amount of product over time. It doesn't matter, again. So remember, we know that the factors are going to affect the rate of reaction. Can anyone list all of them? Let's see if we've got some people in here who can remember every single factor that affects the rate of reactions. Catalyst, surface area, yeah. Surface area, catalyst, temperature, concentration, and catalyst, temperature, pressure, surface area, and concentration. Perfect. Temperature, pressure, presence of catalyst, concentration, and surface area. That is perfect. Okay. So talking about just a general qualitative effect. So qualitative is sort of from words, basically. It's not numerical. We're going to talk about the qualitative effect. So what's happening when you increase the temperature? Well, what you're doing is you're giving the particles more kinetic energy, right? So the particles are gaining kinetic energy. And so if we think about our Maxwell-Boltzmann distribution, because really one of the most common questions you tend to get in your exams is link particle link. So that's a general Maxwell-Boltzmann distribution. Oh, excuse my drawing. I'm doing this on a laptop, so the laptop with a mouse, so it's not particularly good. I'll try and repair that a little bit. That's your general Maxwell-Boltzmann distribution. All the particles are kind of shifting in this direction, right? Because they're gaining energy. So therefore, but remember, we know that the total number of particles doesn't change. Temperature isn't increasing the number of molecules that you've got. That belongs to concentration and pressure. So temperature, all it's doing is it's flattening the curve out. So the peak is less steep, but overall, as you can see, the peak is less steep, but overall, you have more particles with, if you can imagine, that's the activation energy. So before we had X number of particles that had an energy greater than the activation energy. But since we've increased our our kinetic energy for all, should the peak shift more right? Generally, yeah, sorry, that's just the computer drawing. The peak does tend to shift more to the right. I'll try again. It's a bit more difficult to do this. It's like that more than anything. So yeah, the peak does shift more to the right. So that's at that was before, but now after, we've got way more particles. We've got all of these new particles. So therefore, the rate of reaction is going to increase. Yeah. So more particles will have the activation energy. So the correct term will be a greater proportion of the particles, because it's not necessarily more, it's just a greater proportion of the particles have more than the activation energy. And then the rate of reaction overall increases. Does that make sense? So that's your 3-step approach to answering this question in an exam. I'm going to give you a second to write it down. Give you a second to note this down. Cool. So this is kind of your general, again, it's the diagram, it's the same explanation, just in a different way. Again, same, it's just a qualitative analysis of this is temperature reaction increases. Okay, now we're talking about Boltzmann distribution again. So recognizing that, yes, the peak shifts to the right and more particles will have energy greater than the activation energy. So the peak should be lower and shifting to the right. Yeah. So that's the kind of stuff you should be talking about. And then the final thing is increasing the temperature, increases the proportion of samples, particles that have sufficient energy to react, which increases the area of the shaded area, hence overall rate of reaction increases. And then therefore a small increase in temperature leads to a large increase in rate. And that's the kind of essential principle to it. Okay, we're going to move on. I'm going to move on quite quickly because I kind of do want to get to equilibria, hopefully by Q2. So kind of do want to get to equilibria by Q2. So we're going to talk about concentration and pressure. So again, concentration and pressure both work in similar ways. So we need to understand that both of these work in similar ways, and we now need to talk about the qualitative effect. You don't need to worry about this on a Maxwell-Boltzmann distribution, purely because all it is it's just a bigger Maxwell-Boltzmann distribution. It doesn't really change the shape of it that much. Okay, so high concentration increases the number of particles. High concentration, high pressure, again, increases the number of particles, which increases the number of collisions. That's all it's doing. So number of particles within a fixed volume increases, again, because just increasing the number of particles does not do anything by itself if you double the volume, for example. So it has to be particles in a fixed volume. And therefore, particles will then collide more frequently. And therefore, there's an increase in the rate of reaction. Does that make sense? Yeah. Yes, cool. So that's your three-step approach, again, to approaching these types of questions in the exam. And remember, pressure, exactly the same, because pressure is just concentration of a gas, because it's amount of particles of the gas in a fixed volume. So occurs when there's an increase in pressure of a gas, distance between particles is small, particles collide more frequently, increase in the rate of reaction. So again, that three-step approach to it. Does that make sense? Everyone got that? Cool. Last thing is catalysts. So what do catalysts do? Well, their principle is basically a catalyst, first of all, is any substance that increases the rate of a chemical reaction without being changed in chemical composition or amount. So it's any substance that works to increase the rate of reaction, but it itself is not changed. And it does that by providing an alternative route to a reaction with a lower activation energy. And so the temperature needs less energy, the reaction needs less energy to get going, and therefore it can happen at a lower temperature. So as you can see, without the catalyst, you need to get to a higher peak, but with the catalyst, your peak is much lower. It's kind of like, again, this mountain analogy, but instead, if you had a tunnel running through the mountain, that's kind of what it would be. Because it would literally just be a tunnel running through a mountain. So it means that you don't have to go to that higher peak. Remember, catalysts, because they are made and then they're used and then reformed at the end, they are not, the overall effect is that they can be reused. Yeah, so they're not used only once. So remembering with the Maxwell-Boltzmann distribution, what happens? All that happens is there's a change. Remember, the activation energy lowers. So it provides an alternative reaction pathway, lowering the activation energy. So you move the line for activation energy to the right, to the left. That again does the same function as we did with temperature and increases the number of particles with the proportion to be able to react. Now, they've gone a little bit further left, but principle still intact. And so that there's more particles have the sufficient energy, shaded area increases, and therefore the rate of reaction increases. Does that make sense? I'm going to give, we've done that quite quickly. We've run through those last couple of factors quite fast. If you want to explain kind of, if you want to just kind of explain to me your process and your thought processes so far, and any questions you've got for the whole of kinetics. Nope, pretty straightforward so far. Anyone else got any questions? Okay, so we're now going to move on to Equilibria. Again, normally here I would take a short break and just kind of talk about it, but there is quite a lot to get through with Equilibria. We hopefully can get through KC. I definitely want to get through Chatelier's principle before the end of the session today, though. So, okay, so we've talked about, so again, the first kind of discussion is about what a reversible reaction is. So that should answer someone else's question who's asked before, is about what, can you explain forward and reverse reactions? Then we're going to talk about applying Le Chatelier's principle. And the last thing we want to talk about is the Harbour process, all of which, I don't know how many of you did AQA GCSE chemistry, but most of which should have come up in the AQA GCSE chemistry specification. So you need to know 3 definitions. A reversible reaction is one that can occur in both directions. So the reactants can form the product, but if you go back, the products can also form the reactants, which is quite cool. Remember, the direction in which that reaction goes depends on what condition it's been in. And that's basically what Le Chatelier's principle is, the whole idea that it's moving in certain directions and moving in other directions. So remember, we use a double-headed arrow to show that reversibility. A dynamic equilibrium is set up when the forward reaction occurs at the same rate as the reverse reaction, which means, can you tell me what that means? In terms of, can anyone tell me what that means in terms of, yeah. So someone read my mind almost, that the concentration stayed the same. It's like there's no net effect on it. So A is still being converted to B and B is still being converted to A, but they're happening at the same rate. So it doesn't really change anything. So a dynamic equilibrium, A will be converted to B, then B. So overall, there's no effect. But remember, you've said overall concentrations are constant, but this can only happen in a system where you're not adding anything further to it. Because if you were adding anything further to it, then well, then you potentially lose the ability to maintain a dynamic equilibrium. So this is why this can only occur in closed systems where nothing is added or removed. Okay, now understanding what Le Chatelier's principle is. So this is the definition. If a dynamic equilibrium is disturbed by changing the conditions, the position of equilibrium moves to counteract this change. It's kind of the homeostasis of chemistry. It basically is. It's the whole idea that when one thing is changing, we do negative feedback to try and bring it back. Yeah. And so this is really about changes in temperature, pressure, and concentration. So the rules are predominantly these 2. If the position of the equilibrium moves to the left, more reactants will be produced. And if the position of the equilibrium moves to the right, so moves to the right, more products will be produced. We know that, right? If it moves to the left, more reactants. If it moves to the right, more products. Sorry, other way around. No, that was the right way around. Yeah, that was the right way around. Okay, so starting with concentration. So if we increase the concentration of the reactant, we're going to shift to the right, because increasing the concentration of the reactant increases A. And so in order to counteract this, we want to increase B instead. So we move the equilibrium to the right. that kind of makes sense, right? So increasing in reactant because it leads to more product being formed because of that extra reactant being used up. Now, if we decrease the concentration of the reactant, we're decreasing this. So proportionally, this looks slightly bigger. And so therefore, to counteract this increasing, we move to the left. Yeah. Is that making sense so far? Now again, if you increase the concentration of the product, we counteract this because we move to the left, because we want to go in the opposite direction. We want to try and bring the concentration of the product down. And so how do we do that? We convert more of it back into the reactant. Yeah. So increasing the concentration of the product is a shift to the left because it leads to more reactant being formed so that more of the extra product formed is used up. So the opposite effect will occur if the concentration is decreased. Okay, so that's a summary of it. I would like you to take that down in your notes, all of you. I'm going to give you a minute to do that. Yeah, you got that all done? Okay, so pressure is exactly the same principle. Overall, there's no change. So if you increase the pressure, in wherever you increase the pressure, it basically is going to shift to the side with the fewer moles. If the pressure of the system is increased, the position will lift to the side with the fewer number of moles, because remember, concentration works in assuming 1-to-1, whereas pressure doesn't work like that. Pressure works with gases. So it's going to shift to the side with the fewer moles, which will lower the pressure again and bring it back down to normal. Okay. And a decrease in pressure will shift to the side with the most moles. Yeah, everyone knows this now. All right, I want you to put this in your notes as well. Okay, perfect. Guys, let's do temperature now. So an increase in temperature is going to shift to the endothermic direction. So if the temperature of the system is increased, the position will move in endothermic direction because endothermic reactions need energy heat. So those will then remove that extra heat, right? Because if the reaction that requires heat takes all the heat up, then you'll have no leftover heat, bringing the temperature back to normal. Decrease in temperature shifts in the exothermic direction. So if the temperature of the system was decreased, the position will shift in the direction of the exothermic, because exothermic direction reactions release heat. So this is going to release all that extra because this will provide more heat into the system, bringing the temperature back to the back to normal. So put this in your notes. Okay, does one make sense so far? And I'm assuming that this means a decrease in temperature. Any questions so far? We'll talk about catalyst, because catalyst doesn't really matter too much in Le Chatelier's principle. So if you've got any questions so far, this is kind of a good place to ask, basically. Anyone else? Any questions? Are we sure? We good so far? Cool. Let's talk about catalysts, because catalysts do nothing, really. So, oh, what's this? Oh no, this is different. Okay, a catalyst does not affect the position of equilibrium. It affects how quickly the equilibrium is reached. It doesn't affect changing, because what it does is a catalyst increases the rate of the forward reaction and the rate of that reverse reaction by the same amount. So, so there is just no overall change, because the forward and the backward reaction have increased by the same amount. So adding a catalyst has no effect on the position of equilibrium. But it does affect the rate of reaction, as we know, as we discussed in the kinetics topic. It increases the number of particles that are able to reach that, that activation energy, increasing the rate of the reaction by that. So it increases the speed of the forward and backward reaction, does not actually affect the position of that equilibrium, though, because it's doing both by the same amount. It's doing all the work together. And again, catalysts do not affect yield. They do not affect the yield of the reaction at all. Right, so the last equation is understanding, the last sort of learning outcome is understanding the compromise in industrial reactions. So ideally, depending on what your reaction is, you would want to use optimal conditions. So for some reactions, you might want high pressure, high temperature. For some reactions, you might want low pressure, low temperature, but you end up giving a lot of compromise. So I'm going to talk about the compromise for all of these. So I'm going to talk about the compromise for high temperature. Well, high temperature creates a bit of a compromise if even if your forward reaction and the reaction you want to do is endothermic, it creates a high energy need. There's a lot of cost associated with it. So that's going to be a compromise there. It's going to be an industrial compromise. High pressure provides a safety risk. If that's the optimal condition, if high pressure will provide a safety risk. If low temperature and low pressure are the optimal conditions, we don't really want a low temperature or low pressure, because that's going to slow the rate of reaction down. And therefore, we're really balancing this idea of cost and yield rate. And the best example of this is the Harbour process. So the Harbour process occurs in a reaction. Remember, we're trying to produce ammonia. Your forward reaction is exothermic. So high temperatures are going to move it this way. We know that. High pressures are going to move it to the side with less moles of gas. So they are going to move it in the direction of ammonia. So the optimum conditions for this reaction are going to be low pressure and high temperature. Sorry, other way around. High pressure, low temperature. But why do we not use this in industry? Because why would this be a terrible idea? Well, actually, let's see if someone's got an answer to it. Low temperature means low rate of reaction, and high pressure is dangerous. It provides a safety issue. Also, it's really expensive to maintain a high pressure, right? So that's why we end up coming to a compromise, an industrial compromise, which is the idea that we say that we probably wouldn't go too high a temperature, but we would still need a decently high temperature. And a high pressure increases the expense and safety. And so therefore, we use a medium level of pressure. And that's really what tends to happen in most industrial circumstances. There aren't very many that take place at really high temperatures and really high pressures, even if those would be the optimal conditions, purely because they are quite expensive to maintain. Most reactions tend to take place at some kind of middle ground, is an understanding that we reach an industrial compromise with it. So this is kind of the idea that if you want to maximize the rate, you go for high and high. But if you wanted to maximize the yield, you go for low and high. If you want to maximize, minimize the cost or make the cost as low as possible, you go for low and low. But you're probably going to end up going for medium and medium because it's a little bit more complicated than that. Okay, well, I'm going to not do KC. I think I do have another session planned on KC in this semester, this side of the half term anyway. It's going to be KC and KP, so we'll go through it then. Do we have any questions about sort of the AS Equilibria stuff and AS kinetic stuff? If you've got no questions, you're more than welcome to head out slightly earlier. Can we go back to the previous slide? Yeah, of course. Remember that this is only for the Harbour process, because the maximum yield is going to change depending on the reaction. If temperature is increased, then will delta and delta negative. Yeah, because delta negative means that a reaction is exothermic. And if temperature is increased, it's going to want to move in the endothermic direction. So yeah, it's always going to move to the left. Yeah. Delta negative is to do with enthalpy, and which I'd like to teach you guys at some point, but I think again, I've got a lesson booked on it at some point this semester. Don't know. I'm not really kind of certain on this yet. Any other questions? Won't high temperatures maximize the yield? No, because the Harbour process is an exothermic reaction. So high temperatures will move the reaction equilibrium to the left, favoring the production of nitrogen and hydrogen, which isn't particularly good. And that's why I was saying to you, Safa, that this table really only applies to the Harbour process or reactions like the Harbour process with similar conditions. It doesn't apply to every kind of reaction or every kind of temperature available. Yeah. Any other questions? I'm gonna end the session now, ish. Cool, perfect. I hope to see you all on Sunday again. Remembering 3 to 4, there is a biology session for you guys. I will be teaching. Let me get the lesson schedule up. I can tell you exactly what I'll be teaching. I think it's going to be practical design this weekend, so that'll be quite interesting. But I hope you're enjoying these lessons. I will be doing a feedback sheet next week. Oh no, it's DNA and DNA replication. I'll be doing a feedback sheet for Saturday just to get some feedback from you guys, just to see on how I can improve and what you guys are looking for. So if you guys are there, you will get an opportunity to fill out a little bit of feedback for me, just so I know what to do next semester, because I'm going to be continuing these lessons every week after the Christmas holiday as well. No worries. See you guys. Hope this was helpful. Bye, everyone. Cool. I'm going to end the lesson now because I've got to jump onto another teaching thing. So hope that's perfect for you guys. I'll see you hopefully next week or on Sunday. Bye.